Hello there, welcome to a wonderful world of radio frequency and electronics engineering. Hope you're keeping well. On the bench for repair today is an ICOM IC736 radio transceiver. This particular radio transceiver has got a fault where it doesn't power up. You hit the mains power switch and nothing happens. So I've already verified that fault, and we've disassembled the radio now to such a state where we can access all the power supply and rest of the radio to do some measurements. Now this ICOM 736 is a fully featured HF transceiver, and it also operates right up to the 50 megahertz ammeter band, which is a 6 meter. It operates in all modes, which is SSB upper sideband, lower sideband, CW wide and narrow. It operates on AM mode and FM frequency modulated mode, and it boasts quite a significant output power as well, which we'll look at when we look at the specifications and the receiver specs as well. Really nice radio, been around some time. A quite heavy transceiver, a very heavy radio. This is meant to work in an environment where you get mains electricity and not DC as in battery. There are some models in this range, I think the 736 or 738 dash whatever, that allows you to work them with DC as well. Often they'll have that, but this radio doesn't work with DC externally. The reason for that is because the power amplifier module that sits over here on the right operates at 28 volts DC, whereas a radio circuitry itself operates at 13.8. So yeah, the other radios that came after this had the power amplifier designed to operate at 13.8 volts, so thus they could work from an external DC supply, such as a vehicle supply at 12 volts. So yeah, this radio is meant to be powered mains only, that's all, not DC. So it has on the left side here a switch mode power supply, which we're going to be looking at, because when I hit the main switch, it ain't coming on, there's nothing happening. So we'll obviously do the basics, checking the fuse, looking at the connections, doing all that kind of thing as well. So yeah, let's get into it. Okay, so we've got it disconnected from the mains, and we're just going to have a look at this a moment, because just a bit of a safety thing around these type of power supplies, these switch mode power supplies in general. And I'll tell you a story as well about working on this kind of power supply and how dangerous they are. Of course, as we all know, our experienced electronics engineers know, working on switch mode power supplies that are mains operated can be deadly. Very dangerous power supply indeed is a switch mode power supply. It's even more deadly and even more dangerous than any other type of switch mode power supply when we have capacitors like this. And I'm going to tell you a little story about those little capacitors, or not so little as they may be. Many years ago, when I was an apprentice electronics engineer working in a radio workshop where we maintained radio communications equipment in the thousands for various customers, we used to get a power supply in a switch mode power supply that operated a Philips FM1100 PMR private mobile radio, and this power supply was called, I think it was a PRX10 or something like that, and it had a power supply in it identical to this in every way, shape and form. Now these power supply architecture is obviously common. Now, however, this type of power supply has something that's actually quite deadly, and it's very, very easy to overlook it. Even the most experienced people can overlook it and end up half a day with the undertaker if they're not careful. And this happened to me once as this apprentice, repairing, as I'd done hundreds of times before, I think it was a PRF10, sorry, power supply. And this power supply had these type of capacitors in, electrolytics, with the aluminium tops exposed, as you can see there. Quite conductive metal, aluminium, it's no plastic on the top. Now most capacitors that you get in these power supplies are like this, and they've got a plastic cap on the top, thus an insulator. Okay, so cut a long boring story short, I'd repaired hundreds and hundreds of these power supplies over many years, got a bit cocky one day, and I was talking to my colleague in the workstation next door, and this particular power supply that we had a problem where it just wouldn't start, and I've been working on it for some time, and I was just, you know, asking my colleague next door what he thought, because I just couldn't get this bloody power supply running. And basically the top and bottom of it is that I was asking his advice. Now, some of the faults that you get with these power supplies, obviously capacitors, electrolytics, which dry up, and then obviously the power supply won't start. So I'd already replaced these two capacitors in this said power supply. And whilst I was talking to him, and he bent round the divider between us to have a look and see what I'd done, and sort of just give a bit of advice. So I was talking to him, and I actually said, I held my fingers like that, and I actually said, I've replaced these two capacitors. And as I did that, my two fingers touched these two aluminium cans. And the power supply was actually switched off. The mains was out the back. Maybe about a minute. I pulled it out, and then I started having a conversation with him, basically. So the two bleed resistors that are across each capacitor to bleed the charge that's in these when the mains are turned off, the resistance on those was very high, and it wasn't discharging them very quickly, but I didn't know this at the time. So as I touched these two capacitors with my fingers, my God, can I tell you something? I'll never forget it. And it was like as if somebody had grabbed my hand and held it down with such force, I couldn't get my fingers off these capacitors. And luckily the current went through me wrist, and it felt like as if I got Mike Tyson holding my hand down. And no matter how hard I tried, I could not get my hand off those capacitors. And in the end, I just fell back, and then my fingers came off the capacitors. And I ended up on the floor behind the bench, and everybody started laughing in the workshop, as you do. And I tell you what, the pain in my wrist for some time after that. Luckily for me, I'd not burned myself or injured my hand other than just the nerves in the hand. But these capacitors, little did I know, there was a voltage on the cans of the capacitors. Now, I didn't know that would be the case. I thought the cans were insulated from the capacitor material within it. As we know, it's like wax paper, aluminium sheets, interwoven and then coiled up, and then you've got that electrolyte material, liquid that's in them, the electrolytes, the electrolytic, gives it that electrolytic capacitance. So the coil of conductive material and paper and everything's in like a tightly woven spool inside, and then the can, this outer can, is placed over that, and then the bottom part of the capacitor, which is this part, is pressed round it. So in theory the can should be insulated from either of the two pins, but it isn't, because obviously the nature of a capacitor as it is, with the liquid that it's immersed in and the conductive material and the insulated material that forms a capacitor, essentially makes the outer can of a capacitor live. And we're going to demonstrate that here so you can see it for yourself. So it makes it a potentially deadly situation. Now in my case, obviously my two fingers touch the capacitor, so the current just flows that way. However, had I had one hand on the chassis and then I'd had pointed and touched those capacitors, then obviously the current could have gone through my chest and stopped my heart, and it would have killed me. So this is where you've got to exercise extreme caution when you're working with these power supplies. I can't stress it enough. And I see people on YouTube sometimes that repair things. They're not necessarily repairing radio equipment. It could be like a keyboard, a piano keyboard or something, power supplies packed in. And I see people turn them on, find out that the power supply doesn't work or it's not starting up properly, then it shows them disassembling it, and then they literally pick the board up and then touch the undersides of the board with the capacitors and things like that. And it's so dangerous to do that. I mean, most of these switch mode power supplies that you tend, the smaller ones, have very small electrolytic capacitors, far smaller than that in some cases. And so, maybe they're not as dangerous when they're being disconnected in terms of how long that capacitor stays charged for. But it's certainly the case that in some power supplies I've worked on, the bleed resistors that are across the capacitors can actually go very high in value. into the megohms range, because they've had years and years of being turned on with that current across those resistors, and it just makes the resistance go high. And so even on some capacitors like this, where the bleed resistors are okay, when you unplug the mains, those capacitors can hold a charge for a very long time. Sometimes they can hold capacitors for days after the unit's been switched off, enough to give you a very nasty shock. So in this scenario here, we could be making a measurement down here, and we could have our hand here thinking, oh, and just go across and touch those capacitors while it's turned on, which is even worse when there's mains connected in, and you aren't going to know about it big time. Now, especially here in the UK, where we have 240 volts RMS, by the time it's smoothed by these reservoir capacitors after rectification, you know, you're talking, you know, a lot of voltage there, in the 300 plus volts range. So you're going to get that kind of voltage there, and you're going to get a nasty surprise. It's even worse potentially as well than AC, simply because it's DC, and that's where I talk about that grabbing, where I felt like my hand had been grabbed and held down forcefully, because DC does that to you. AC gives you some chance to some degree to remove your hand. It sort of shocks you in such a way that you can, if you're depending on the voltage, you can throw your hand off quite easy. However, DC, it makes you actually grab it, you know, the conductor harder with you. It tightens your muscles up. So that's what happened to me. Fortunately, when I work on these power supplies, I tend to work one-handed. So if I'm doing any work, I always have the other hand in my pocket or on my leg. So if I'm working, I'm only doing one-hand measurements, and that's for a very good reason, because obviously then you haven't got the other part of your body touching the chassis. You're obviously not introducing another hand that could touch that capacitor in that one, or something live and something over there that's neutral. You know, you're minimising the risks of causing yourself a very severe electrical shock, if indeed a fatal electrical shock. So let's prove this. Let's turn it on and provide power to the circuit, and we can show on the meter what kind of voltages we get on these metal cans. So I'm not an advocate of having switch mode power supplies fitted with this type of capacitor, although they're a good make. I mean, they're a Rubicon capacitor, you know. These are not cheap rubbish. These are good quality makes of capacitors, but with the aluminium can being exposed, it's a danger. And when you look at these capacitors, obviously these are a lot safer. They're not 100% safe, but they're a lot safer than the aluminium can, because these tend to be a plastic outer now. These tend to be a plastic jacket, like a nylon, and then we've got a cap on the top as well. So they're all plastic, a lot of these, rather than aluminium. You do get some though still, even to this day, where there's still an aluminium can, but there'll be a plastic shroud over the aluminium with then a plastic cap. So these are a lot safer to work with in terms of touching than you would do if you were, you know, obviously touching the cans on there. Not many people expect, you see, to get a shock off a can of a capacitor, especially when it's just been turned off. But you know, they would expect if you touch the terminals on the bottom of the capacitor to get a shock, obviously, but not the metal can. So this is a word of caution to anybody out there who's working on any switch mode power supply. It's in a television, a video recorder, it's in a Sony PlayStation, you know, whatever it may be. If it's got a switch mode power supply, you need to exercise extreme caution, even more so if it's got capacitors like that. If you're working on a power supply like this and you couldn't remove a power supply from the unit in order to work on it because of some other limitation, it's always advisable to put tape over these. That's what I would do. I would tape them off to insulate so that there's not much of a risk of accidental, because while you're making measurements, it's so easy just to forget yourself just for that brief second, and that's all it takes to make a fatal error. And it's the same with the main switch as well on this. You know, we've got live and neutral connection here from the mains input going straight to this switch, and these terminals are not insulated, they're exposed. Again, you know, it's easy, you think, oh, I'll just turn it round, and then you put your finger or your thumb on those, you know what I mean? As you're turning it round, you do that, and next thing you know, wham, you're going to get a real surprise with that one. So always be cautious. It's very, very easy to forget these basic safety facts, and it can cost you your life if you're not careful. Always treat electricity with respect. Even the most experienced engineers can come a cropper, because you get overconfident and you think, I've done this 1,000 times before, and that's when you make your mistake. So let's have a look at this a bit further now. Okay, so we're ready to do some measurements now of what's on these capacitor cans, not the terminals, but the cans, and against between the chassis and the cans, to give you an idea what kind of electric shock potential lay within. So I'm just going to make sure that main switch is on, so we can introduce the mains cable. Now, because we potentially could have a maximum of around about 340 volts DC peak on these capacitors, particularly on the terminals underneath, the multimeter here has only got 1000 volt and 200 volt range on this cheap old multimeter I'm using here just to demonstrate this. So I've got it on the 1000 volt range in case it's higher than 200 volts so it doesn't damage the meter. Now obviously the mains 240 volts is the RMS, and to calculate the peak you just multiply the RMS voltage by the square root of 2, or in our example we could use 1, multiply it by 1.414. So basically it means that you're going to get about 340 volts peak across those capacitors after the bridge rectifier. The bridge rectifier is clipped to the heat sink down there. There's a square bridge rectifier bolted down to the heat sink. So let's do some measurements. So I'm going to connect the mains in now, and we'll do that. So it's now on. We'll then go on to the capacitor cans and have a look at what DC voltage we get there then. So we've got 148 volts DC there between can to can, between chassis and the can. So that one there we're not getting anything on it, and this one here we're getting 124 volts. So it's easy to see the severity of electric shock you could potentially receive. Bear in mind it's DC voltage as well. So if you went between the chassis with your hand and that there, you're going to get 125 volts. And as well as that, if you bridged across both electrolytic capacitors and the chassis, you're going to get a nice 147 volts added on top. So you're really going to be in for a very, very nasty surprise. And I mean nasty surprise. So that is just a fraction of the voltage which is actually on the terminals underneath. So there are two dangers if you think about it working with this power supply. You've got that danger, okay, and you've also got the 340 volts DC danger when you're then doing measurements on other parts of the circuit, simply because that's the mains potential after rectification peak voltage that's going to be present on the components like the switching regs down the side there and other components. So extremely dangerous. So let's also do another measurement here. Let's put our pros back on the capacitor and let's remove the mains input and see how long it takes to discharge. So the mains input's removed already. We've got like 130 volts. So by now anybody who's inexperienced might be turning this round. They could be touching inside ready to make, you know, move cables, and then already they could get a massive shock even with this connector, because, you know, you're talking well over 100 volts you know, potential on there. Not good, not good. Even now after all this timing, 80 volts coming up to. Now you'd normally with DC start to feel quite a bit of an unpleasant shock around about 60 volts DC. Anything below that you might get a little tickle, but generally speaking, depending on how moist your hands are, what things that, you know, conductor you're touching and how well you're touching it, it depends on the severity of the shock. But bearing in mind, you know, if you've by now after all this time been messing about inside it while you've unplugged this thinking that everything's safe, you're in for a rude awakening. So that's the danger really, isn't it? The fact that you've got all these live parts even after the connection has been removed, the mains input. So very, very nasty indeed. So that's why you've got to exercise caution. Obviously with the way this is constructed with high sides and back and front, it's going to be very difficult in order to work on this unit, even to measure voltages down there on the circuit board level when it's actually powered on. So again, there's more potential danger there. So it might be worth removing the power supply from the radio so we can work on it on the bench if need be, in a more safer working environment than we would if we tried to work on it while it's in the unit, and sometimes it's better to do that. Now, in terms of what we're going to do now, we're just going to give it a visual once over next with the camera. We're going to have a right good look at it and see what components in the power supply might have gone frazzled, barbecued, and then we're going to then look at we're going to look at the circuit diagram anyway now to see how it functions and what components are doing what, and then we get an understanding as to how it works before we proceed any further and what kind of voltages are going to be coming out. Now I can also go on to this DC connector here, which is the output. I think this is a 28 volt rail that goes to the power amplifier section, the high current power amplifier section. And again, are we getting any voltages? We're not. We're getting nothing coming out at all. There is another cable which goes down the right side here. You can just see down there underneath this red, next to the blue, these group of red and black cables. That, I believe, is the 13.8 volt low voltage side that goes to the radio circuitry. However, the 28 volt rail goes to the power amplifier. Because this model is the ICOM 736, which just works off of mains voltage only, and there's no DC connections on the back. However, on the 738 model, then you've got a DC jack as well. Now, this isn't for power, this is for the tuner. Some people think that's the power socket. It isn't, it's just for the tuner. So this is a mains only radio, simply because the RF power amplifier section works at 28 volts DC, and the radio section itself, receiver and transmitter exciter and all the other circuitry for the tuner, works at 30.8 volts. So this is why you got this separate 28 volt power rail that's going off to feed this. So that's an explanation of that. So let's have a look at the schematic diagram now and see how this power supply works. Okay, so let's describe now how the power supply works. So here we've got what is a circuit diagram that's broken into like 3 different pages. So we'll cross from one page to the other as we describe it. So just down here we've got the AC input, the live and neutral, which comes in through a transient suppressor. We've got an X-class reefer capacitor, C1 there. X-class goes between live and neutral, whereas Y-class, which are these capacitors here, go between either the live and the neutral and then to ground. So they're Y-class capacitors, these are all X-class that are across the live and neutral. So the mains comes in through a transient suppressor, it also goes through a reefer capacitor. We've then got L1, which is an inductor filter, which conditions the AC line coming in, but also is bidirectional in terms of preventing the switching frequency of the switching transistors at the frequency that the switch mode power supply is switching out from escaping onto the mains. This is all part of EMC compatibility. We've obviously got another reefer cap there for filtering, and then we've got the Y-class reefer caps, which are C3 and C4, which then go through some more capacitors to chassis, ground chassis, because the earth connection from the line from the mains connects to chassis as well. We've got R2 across their resistor, then we've got another inductor L2, another filter. Then we've got this device here, which is R1. Now this is an inrush resistor to protect the power supply from when it's turned on. It's obviously going to be charging up these large electrolytic capacitors. Now these are those great big can electrolytic capacitors we were talking about earlier, where there's a big shock potential here. So to limit the current to the circuit as these charge up initially when the mains are switched on, you have what's called an inrush current resistor here, which allows the capacitors to charge at a much slower rate, thus limiting the current flow, the inrush of current to charge them, so it doesn't blow the power supply up or the fuse. Now you'll see across it there are two connections coming off here, off of R1. This goes to a relay contact that we'll see very shortly. Now normally on most power supplies that device there will be an NTC, a negative temperature coefficient resistor, and so initially when you start the supply and the inrush of current goes through it to charge these electrolytics, that resistor would warm up essentially, and basically it would allow only a limited amount of current flow to then charge these capacitors. But once the capacitors have charged up fully within a few milliseconds of being switched on, then the current going through the resistor is far less, so the resistor then allows more current to pass through it and thus ultimately carry on supplying the circuit. Thus you wouldn't need a relay contact, and that's what most power supplies, switch mode power supplies have. However, in this case they've decided not to employ an NTC, they've decided to employ a relay contact, which just basically is like a soft start mechanism. When the power supply is switched on and giving an output, the relay then would close its contacts and short this resistor out, thus allowing the full amount of current to be passed to the bridge rectifier. So we'll come back to that bit of the circuit a bit later and explain how that works, how it then shorts this resistor out to allow full current to the supply. Because obviously without that shorting of the resistor out, with it being a 10 ohm resistor, by the time we've loaded the output of the power supply and the current draw that comes from the live and neutral, this resistor will get very hot and melt or burn out, so it has to be shorted once it's done the initial charging up of the capacitors. So what we'll do now, we'll look at the bridge rectifier. So we've obviously got the one side of the mains going to the bridge rectifier directly there, and then here on this side, which is assuming going to be the neutral side, goes to WHC. This is a jumper which can either go either left or right. So if we want 240 volts operation, this jumper goes there. If we want 120 volts, it goes there, and it goes in the junction of these two capacitors. So that's how that works. So in our case it'd be 240 volts AC RMS, which will connect there. Now the output of the bridge rectifier, which is the left and right connections here that go to the reservoir capacitors, this top line here going round is a positive, and this line here is a negative. So peak voltage now, we would be looking at round about 350 volts DC, approaching anywhere between 340 to 350. So yeah, that's what peak voltage we're going to get across there. Very, very dangerous indeed. And with these capacitors storing the charge as well at DC, then ultimately that's definitely a killer voltage, is that. Half a day with the undertaker if you start messing about with these lines and you touch him with your fingers. So we've got bleed resistors across both capacitors as well, which when the supply is not on, each resistor in turn discharges the capacitor. It's a quite high value at 330k, so it will take some time to do that. And then we've got the lines going off then as well, so which then supply 350 volts DC to the rest of the circuit. We've also got, as you can see here on the negative side of these reservoir capacitors, a line coming down here to two more capacitors in series, then an inductor. This is a frequency trap, so this is tuned to the resonant frequency of either the line or the switching frequency of the power supply. So any noise on this negative line here from the power supply will then go down to ground and be suppressed that way, so it won't make its way out back to the mains input. So that's also a bit of EMC compatibility going on there. Now if we go to the next part of the circuit, which is here, we can look at then how this potentially starts up this power supply. This line here is a continuation of the top of that capacitor, because these two big electrolytic capacitors just off the left side here. So that's a negative line, that's a positive line, 350 volts DC across these two. So it comes along here, and as you can see we've got a 100k resistor, this R7, and this 100k R8, and then we've got another one which is R16, a 22k to what is the negative line. So you could see this resistor here, these two, as being one resistor at 200k with a junction in the middle for R16, which is a 22k. So we've got a potential divider there. If you notice as well, we've got an electrolytic capacitor C10 at 47 microfarad, and we've got what appears to be a secondary winding of the switching transformer here, which appears again to supply some kind of power, which we're going to discuss in a moment. But I think how this supply starts up, with the look of it, is the 350 volts DC gets broken down through these resistors, reduced down. This is a potential divider, so we get a much lower voltage here on this line. That then comes down to this IC, which is the pulse width modulator IC, the main switching IC that switches the FETs, which ultimately are these two, and this in turn switches the primary coil on the switching transformer. So these two FETs effectively switch the 350 volts DC, a high frequency, through the primary coil on the switching transformer. So the drive from that comes directly from this IC. So one can assume that what happens is that 350 volts DC comes down, gets dropped by these resistors. This capacitor here, this C10 at 47 mic, is charged up at the voltage that's on this potential on this juncture here. That then goes into pin 20 of this IC to power this IC up. It's also clamped by this Zener diode ZD21. So this ensures that the voltage can't go above a certain threshold and thus destroy this IC. Now at that point, this IC with the RC constants that are around it on these other legs will start to give an output on pin 19. This then will ultimately then drive the two FETs, which are the IRFPE 40s, Q1 and Q2. So these will get driven and start switching, and this then ultimately will start switching this coil here. Now this is a secondary winding here. There's effectively two secondary windings. This is the main secondary winding that derives our main output supply for the radio. However, this is like an auxiliary secondary winding here, which what would happen is once this picks up the switching action of this transformer as a transform effect, couples onto this luxury secondary coil, this diode here will rectify that switching frequency at much higher current than is currently being provided by this potential divider of R7, R8 and R16, and then give a much higher current output then to continue driving this. And that's then when it takes over, because it started then. This circuit here just starts it with these resistors and that capacitor, but once it's got chugging away and it's started, then this takes over and supplies power then to IC21. So the main supply for IC21 is derived here, okay, not here. So this then starts to switch, and ultimately then the output on the secondary of T1, which is a switching transformer, is here. We rectify that switching frequency using these diodes. This inductor here, we've got some smoothing capacitance on the output, some electrolytic capacitors, and then ultimately we've got some Zener diodes here that set voltage thresholds, etc. We've got the optocouplers, we've got two, we've got PC1 and PC2. This is PC2, the sender and the receiver optocoupler parts for mains isolation, because obviously the hot side, the main side, is all on this side of a circuit, and the output low voltage side that needs to be isolated from the mains is on this side. So we have the optocoupler for feedback, and then we've also got another optocoupler which the sender is just slightly off this diagram, and we'll see it. Actually it's there, look, PC1 sender to there. So as this gives an output here, this actually gives two supply rails, which we'll see shortly, a 28 volt rail and a 13.8 volt rail. So the 28 volt rail, which is coming off here, goes through this circuit here. We've got a voltage reference. This is a precision reference, is IC51. So this sets a specific voltage, which then illuminates the optocoupler PC1's sender, and that then couples back to PC1's receiver, which then gives feedback into this switching IC. So this voltage reference IC51 sets the conditions for the sender, and the receiver then knows what the voltage is on the output then of this circuit. So that way the feedback, the voltage feedback, for what is like a controlled loop, a lock loop that goes round, is derived from this optocoupler. So if a voltage changes and it can't regulate, for example, because of some load condition, then this sender will change its illumination, and obviously the receiver will get that feedback and then make some changes. The IC will make changes then to the switching of these two transistors, and it will alter the pulse width modulation, or the mark space ratio, the time in which these FETs are on versus the time in which they're off in the switching cycle, and thus that then will either induce more current in the secondary or less current, and so therefore, depending on how hard the supply is being loaded, will govern the regulation control that way. So we can see that the 28 volt rail is being set by IC51, and PC1 is the sender receiver optocoupler. Now we've got some derivative here of this supply coming down this line here and going via L53 into Q51, which is obviously a FET. And then if we look down here, we've got another Zener diode here setting some kind of voltage reference to this circuit here, which is Q81, which drives Q51. So this is like a, if you like, a Darlington arrangement where we've got a current driver and then a series pass element. So this looks like as if we've got another circuit here, another regulator IC here for controlling that side. Now this in turn could either be a DC regulation, or this also could be a switched frequency as well. So we'll look at that in more depth now. So we can see that we've got the 28 volt rail going off there, and then we've got a 28 volt supply to Q51, where we obviously get some more regulation. We can see as well we've got PC2 sender, optocoupler sender, and PC2's receiver, and we've got Zener diodes here that set the voltages for this condition. So if we go on to the next diagram now to better understand how that works, we've got here the 28 volt rail continuing on. We looked up to here last time, if you remember. There, that's where we got to before it disappeared off the end of the diagram. If you notice as well, we've got a potential divider and we've got VR51, which is a variable resistor, and this allows us to set the output voltage of a 28 volt rail, the supply accuracy, and so in turn that sets what would be an adjustment to IC51 to adjust its output accordingly, and thus it would have an effect on the optocoupler sender, which would then give a different feedback then to the pulse width modulator to then drive the supply differently with pulse width modulation to then alter the voltage on the output. So VR51 sets the 28 volt rail. We'll find that on the circuit board on the mains power supply. We've obviously got some more electrolytic capacitance in after a series inductor here, which again, all these filters like L51, L52, C53, 54 and C55 all filter out. They're designed and calculated to filter out the switching frequency from the secondary winding of that switching transformer, so we get a nice steady 28 volts DC going out, smoothed and noise free. We've again got some more capacitance on the output down to chassis to filter off any high frequency components that are left over. So as you can see, that's achieved by these filter arrangements. Now we'll notice there we've got a tap coming off a negative line and another one coming off a positive line, and it sort of disappears, doesn't it, and comes this way over the top. Now if we go back to that circuit we were looking at on the input, these are the two lines here that are coming across back, and they go across that resistor R1. They are the relay contacts which short out, if you like, the power supply's 10 ohm input inrush current limiting resistor. So this is a relay here, RLY1 on the board. This coil here is energized by 28 volts DC, which is achieved on the output here, this section of the supply, and then the relay contacts close, and ultimately then when the relay contacts are closed, once we've got 28 volts, this resistor gets shorted out. So that allows then full current from the mains to be available to these capacitors thereafter. So when we go back to here, now we've explained that part of the circuit, we've then got, obviously, as we just described a moment ago, supply going via L53. 28 volts arrives at this FET Q51, and as we can see here, we've got some magic going on with this IC81. We've got lots of Zener diodes around this component, and then which controls Q81. So Q81 is controlled by pins 8 and 11 of IC81 via ZD81, which is a Zener diode. This does look like to be a 15 volt Zener diode, and basically this biases Q81, which is an NPN transistor. This then supplies approximately 0.7 volts less between the base and emitter on here on pin 5. So basically it's a series pass element. This then drives the FET, and the FET in turn then is driven to such an extent where it can give 13.8 volts output. So that 13.8 volts output then is fed via L54 again, and then we've got this choke here. So we've got some capacitance on the output, which is C58, another electrolytic capacitor, then another filter, L64, before it's then given to the output here. Now if we look here, this does look to me as if there's some feedback arrangement here coming down and going back into pin 15. So this circuit is essentially self-regulating, if you like, and this is solely separate from the rest of the circuit that we saw earlier in terms of its feedback and monitoring. Now this resistor down here, this variable resistor VR52, which is this one here, that does the 13.8 volt supply accuracy. So by adjusting that, you can then finally adjust the 13.8 volts output. So this essentially, this device then regulates Q81, which regulates Q51, gives an output, and ultimately then there's a bit of feedback there which comes on the junction of this capacitor C57 and another electrolytic cap, comes down, and then via potential divider to ground, and this variable resistor, this pot potentiometer. Now that input to this capacitor and that feedback loop coming down there is derived from a voltage reference, which is obviously ZD52. So this sets up, if you like, a voltage reference for this circuit to operate for the 13.8 volts. Now the 13.8 volts feedback, and what's going on with 13.8 volts feedback, again, we've got an optocoupler sender, PC2 there. So we had one for PC1 there, the optocoupler sender for the 28 volt rail. We've also got one for the 13.8 volt rail, which is PC2. So if this rail starts to get loaded, the output there 13.8 volts, and it can't maintain it, etc., then ultimately that PC2 gives a reference back, if you like, a feedback back to this PC2 here, which is obviously, we can see it there, and that ultimately gives another feedback in pin 8 there. So it's getting two lots of feedback, is this IC, from both the 13.8 volt rail and the 28 volt rail. As you can see, that's a 28 volt sender, that's the 13.8 volt. So both supply lines, the 28 and 13.8 volt lines, are monitored via these two optocouplers which feed back to this IC. And that's the lot, I think, with the look of it. So now having described all that, if any of these electrolytic capacitors have gone dry or leaked, then it's going to cause major problems. The circuit won't start and run properly. Likewise, if the startup circuit here, this capacitor C10, this 47 mic, if that capacitor there is dried up and not functioning properly, the current that's required to drive this IC21 which ultimately directly drives on pin 19 these FETs. If that capacitor is not charging and not available with its capacitance, the current flow through this 200k resistance in series down to pin 20, it's not going to be sufficient. It's just not going to keep this IC running. With that C10 being fully operational, then there'll be enough current while this starts switching for that to be maintained initially to get the circuit going. But that C10's got to be in good condition. Once the circuit's got going and it's switching here, and you get fat feedback coming via this diode, which then energizes this and then gives more current to this IC, you know, then it's gonna maintain its regulation. It's going to start up. That's basically what we're wanting to achieve. We're going to get it to start up. But at the moment it's not starting, so I think there's a problem perhaps with this capacitor. There could potentially be a problem here as well. There could also be a problem with R14 as well, because the supply to the transformer isn't switched. It's the ground path from the transformer to the minus supply rail which has switched. So in essence, it's the high voltage is on this top part here. It's switched through the FET to ground via R14. So if that resistor R14 is going to obstruct, which is a 0.1 ohm resistor, then neither of these two FETs will be able to switch, because ultimately they'll be down to you know, they'll be floating in essence and not down to the ground path. I think the main current as well, or what will be the fallback protection, seems to be, it uses R14 as a current shunt, because we've also got on the outputs to ground before the R14 we've got a sense line here going on pin 19, another capacitor, another resistor, so we've got potential divider here. And so if these transistors are driving too hard because they're trying to maintain an output current, you'll start to see a bit of potential difference across the junctions of R14 and the FETs and the minus line, and this will then induce a small current, small voltage in this line to pin 19, which will ultimately tell this IC how much current this circuit's switching at and delivering to the primary of this coil and thus the secondary, etc. So that's another bit of feedback it gets there to maintain, you know, if a current on the output gets short circuited, and these are going to start driving quite hard, obviously to try and maintain what is a short circuit, the switching is going to be quite vigorous at this stage, and these transistors are really going to suffer. So obviously R14's there to sort of balance that out and give that bit of feedback. So this then might decide to shut down because it can't drive that level of current, and it'll switch off the drive then to these two FETs. So that's potentially how that can monitor the current flow, because there doesn't appear to be much other than that. There's nothing else really that I can describe there, I don't think. I don't know if there's anything else that we can look at. So let's have a look at the capacitors on the outputs. Let's have a look at that capacitor there, which is this C10, this little 47 mic capacitor, which I think is at 50 volts as well. That it's not 300 odd volts, it's only a 50 volt capacitor is that. But again, if that's stuff, then it's not gonna provide enough juice for this to start running. So there's all sorts of little things we can be looking at as well. We can have a look at the R14, make sure that's not open circuit. We know that we've already got the voltages to the big electrolytic capacitors there, because we're recovering a voltage there earlier, and I've checked that off camera as well. I've just gone across the output of the bridge rectifier just to make sure. We've obviously checked the fuse as well, the main fuse at the back of the radio, just to make sure that's not blown. Obviously that's where you would always start anyway. So yes, there's a few things around there, isn't there, that we can have a look at, but I definitely think this startup circuit here is definitely something that we need to look at first. It can also be as well that the optocouplers themselves, the senders, are burned out and not working properly, or the circuit that feeds them has got a faulty component, and it could also be the receivers on the optocouplers. They were the yellow devices on the board we were looking at earlier, the like little yellow 4-pin devices. These are common failures on switch mode power supplies, the optocouplers, opto-isolators. So it depends, it could be anything. So let's start doing some checks and see what we find. Okay, so let's just have a look at some of the components and describe what they do. So up here we've got the line in up here, and this then are the mains conditioning filters. So we've got that as inductors what we described, the reefer caps, etc., and the X and Y class capacitors on the mains line conditioning. That's R1, which is a cement resistor. That's what is the inrush current resistor, what we described, that 10 ohm resistor on the input to the bridge rectifier that we'll see in a moment. That's a relay that shorts out R1 when the 28 volt supply comes up. This gets energized and shorts this resistor out so that it can supply a full current then obviously to the bridge rectifier. The bridge rectifier is located here on the side. Obviously we know about these two big electrolytic caps there on the output of a bridge rectifier. These two are the FETs that switch the transformer, the main transformer for the main switching power supply. So they're the FETs. The R14 that goes in the ground path between the FETs and the negative supply line, if you like, for the capacitors is this. That's the R14 there. If you want to see the potential divider, if you remember we're looking at the excuse me, if you remember we're looking at the startup circuit, how that functions. That's these two resistors here. So as you can see, those two resistors are significantly large. These are 100 k's each, and then that's R16. So if you remember, this came from the 350 volt rail through then to the junction of this capacitor with this resistor, and as you can see the resistor R16 that's across this to ground on the other side. This is the negative side of that capacitor, that 47 mic at 50 volts capacitor there. This negative side of this essentially connects to the negative side of this supply rail from the bridge rectifier and these capacitors. So this is a start circuit, is that. So worth checking that capacitor, removing it, etc. Obviously if this resistor R14 are going to open circuit, then effectively the FETs and the transformer are floating at 350 volts. They can't find a path to negative to or ground path to switch the current. So that R14 there has a 0.1 ohm resistor, so obviously it's imperative that is fully functioning. What else have we got? Oh yes, I can see down here we've got the optocouplers. So if we just have a little look down there, the two yellow devices, these two here, that one and that one, they're the optocouplers, send and receivers built in. Then we've got the diodes that rectify the main supply, the 28 volts of these here bolted to the heatsink. So these are the rectifier diodes on the secondary winding of this switching transformer. And then we've got various toroids, as we can see, which were the inductors we saw in the diagram for the output supply conditioning. We've got capacitors as well on the outputs of the supply in order to maintain the output voltage at the correct level, and the DC make it so that there's very little switching frequency available on the output, and obviously smooth that off. We've got some more capacitors down there that are hidden under there. That's the mains, the IEC input connector, which has got a EMC filter in it, a capacitor between live neutral and earth, and got some inductance in it. So there's an EMC filter in there as well. And if we just turn it round a bit, the main regulator transistors, which effectively do the 13.8 volt rail, are just on the side here. So that's what this is. So if we just shift that over, so we've got one of these is the main FET and the other's a driver for it. If you remember, we had that 13.8 volt circuit. We've got a potentiometer down here as well. That's the potentiometer that controls the 13.8 volt rail. That's a little satellite board which is the regulator section for the 13.8 volt supply and the 28 volt, and controls all the feedback etc. via those optocouplers. And then the other potentiometer for setting the 28 volt rail is actually just on the other side. You might be able to just see it down there. That's the 28 volt rail adjuster pot down there. So you can see there's quite a bit there that we've described, and I think that should give you a little bit more. Okay, so what we've done now that we've got this out the unit and we've looked at the diagram, these two resistors here are the resistors that are in series with the 340 volt supply across these two capacitors, and then goes down to an electrolytic capacitor that was in the board down here, which is a 47 mic capacitor which I've removed. So what I did, I've just lifted this one end of this resistor up, and then I'm measuring to make sure that we had that like 200k resistance. So we had, if you remember, we had the two resistors, then we had the third resistor which went to effectively the 0 volt connection, and then we had here on this juncture we had a capacitor, and then this junction went off then to the IC, okay, which the pulse width modulator IC. Now this was the 340 volts DC line, and so what I've done, I've lifted this end here so we can measure this entire resistance from here to here. So I'm just we've lifted it there, and we're putting our multimeter just across there in ohms, just to make sure that those two 100k resistors in series with one another are actually measuring 100k. And I'll come to the capacitor in a moment. So put it on the 200k range, and then we're going to go from one end of that resistor to the other end, and if I can, we're just under the 200k mark. So those two resistors, these two are okay. So then I removed the capacitor that was either 47 microfarad capacitor, and I've just had that on the LCR meter here, and it wasn't reading anything. It was reading open circuit. So that's not going to do us a lot of good at all. It's going to cause untold problems if that's the case. If it's true, that is, this reading, that it is definitely open circuit and no capacitance at all. So yes, it's not getting anything at all, and unfortunately, yeah, there's nothing happening. So that capacitor's gone. So basically, with that capacitor screwed, what happens is when this voltage gets to here, and this potential divider to drive this IC, because the initial current that it needs to start and then obviously drive other things, it's going to take quite a bit of current, and that's suppressed by this capacitor to some degree. So basically, without the capacitor, when this IC tries to take current to drive an external FET device, which is what it's doing, it's driving two power FETs, then essentially this supply will collapse. So it will essentially kill it every time it tries to give an output. So this capacitor is quite pivotal in the initial milliseconds of startup when the circuit's energized, where the storage of charge in this capacitor helps keep this in abeyance, this line here, this supply line. If there's no capacitance, then the supply line collapses every time it tries to drive something external. So this just is in circuit just to give enough oomph, if you like, enough EMF, electromotive force, in order to make this IC perform initially. And then once this very first pulse kick of the pulse width modulation output to the two power FETs starts, the process of the switching transformer going, then we obviously had, if you remember, when we're looking at the circuit description, we had a diode, and then that went to what was the coil. So ultimately, as soon as this picks up an EMF from the resulting oscillation starting up, then immediately within the very first tens of milliseconds this is going to start and conduct voltage through it, much greater current anyway, and ultimately that then is going to take over the supply. So instead of the initial supply coming down in that direction to then ultimately come in this direction, then once that kick starts, then we get the main supply coming this way then, and that essentially takes over from this in terms of current flow. So this capacitor is quite important. Now this capacitor is DUF, and so we are definitely going to be replacing this capacitor, which is I think it's a 47 microfarad at 50 volts. So yeah, we'll definitely have a look at that in a bit more detail. But yeah, that's certainly something I didn't expect to see, is that gone. It certainly has no sign of any leakage on the PCB or around the capacitor. Normally get like a greasy, fish smelling sort of thing, and just having a smell at it, it does smell a little bit like it's leaked something. So, but yeah, so it might be worth us removing as well the other capacitors anyway, seeing as we've got the unit out, just to check the other capacitors round are okay, and may even check these capacitors as well. It's be unlikely these will have dried up though, to be quite honest. It's mainly the smaller capacitors that tend to dry up. But yeah, so onwards and upwards. Okay, well, I'll just remove this capacitor just to test this as well on the output, and this is meant to be a 35 mic at 35 volts or 8000 microfarad. Now, although it's reading that, it's actually reading 900 and something. It's varying all the time on the LCR meter when you touch it with your fingers. It's obviously not right, and you can see the shininess just there. That's some liquid that's leaked out of it, and if I can wipe it away, you see that wetness. So that's definitely been leaking, and you can see on the board down here as well, look, there's a bit of a puddle just there where the capacitor and plus sign is, and I'll probably be able to wipe that away as well using this, and I can, as you can see. So yeah, that's definitely been leaking. So I think it's fairly obvious now that we've found that obviously all these capacitors are on the way out one way or another. So I think we'll have to do just a blanket change of all the electrolytic capacitors across the entire unit, and I will remove these as well and check them for leakages. But yeah, I think that's the best thing to do at this stage, is to replace all the capacitors first before we do anything else, because it could just be down to the capacitors not being working properly, and thus it won't start if the capacitors are all reading weird values, especially that start capacitor that was down there that we looked at just a moment ago. So I think, yeah, it's what makes sense now to start replacing them, and then see where we get to. Okay, so what we've done, we've replaced all the output capacitors on the power supply, because when I took them out to test them individually, I noticed that they were all wet underneath, and we got the like a little wet mark. You can just see it there on the right hand side of that rubber thing. There's a wet mark there, you see, and there was a mark like that on the board. So I looked at all the capacitors and they were all like that. They're all wet, like that one is there on the right as well. You just see it there on the left a bit better, but that little wet patch there. So although it wasn't a puddle round the bottom of the capacitor, that one had some leakage as well, which you can just see there on this bottom side. So anyway, top bottom of it is I've replaced all the capacitors that were associated with the soft start circuit, where the startup circuit rather, and also the output electrolytics, which there wasn't many actually. There was a few more as well, which I've got over here on the other side of my bench. There's that one there, look. Again, that was leaked quite badly. You can tell it's all wet. And so although it wasn't evident from looking above down, you know, there was no leakage that you could see and no puffing up, you can see there they're all wet underneath, you know, they've all leaked their electrolyte out of them, you know. So anyway, what I've done, I've decided rather than trying to test the power supply off the bench, what we'd do is we'd put the power supply back in the unit, which I've now done. I'm just going to monitor the 28 volt output, which I believe is from this connector, because the other connector goes to the front here and connects the 13.8 volts to the front panel, whereas this is the 28 volt line, I think, which goes off to the RF power amplifier. So what we're going to do is we're just going to see what happens and turn it on and see whether it powers up. So what I'll do now, I'm just going to have a look here to see whether the voltmeter will tell us the output. So we'll just connect mains up to the unit, which I'm just going to do now. So we've got it all connected up, just plug it in. So now we've got mains going to those rather large electrolytic capacitors there. So I'm going to turn it on. And wonderful, got an output 28 volts, look, seems to be working. We've got some power coming out, which is nice to see. That's always interesting, isn't it? So obviously replacing those capacitors has fixed the power supply, so it all seems okay. We'll obviously do some testing with the radio transceiver to see what it does on transmit, and thus put the power supply under load. We'll see what happens then, but that's a very good sign. I'm very pleased. So it's not often that happens to me, to be honest with you. That's a bit of good luck, because quite often what happens to me is that there's a very rare IC that you can no longer get anymore on the board that does a pulse width modulation, and you can't get it in that package style anymore. And some of the components that are surface mount on those little satellite PCBs that we saw that were plugged in on the main power supply will probably be obsolete. So you can end up going off down these rabbit warrens where you can ultimately find yourself not being able to repair the power supply because you can't get the parts, etc. So yeah, that's a really good result, is that. So it just shows you the first thing to start with, I suppose, is if you get any switch mode power supply issues, even if, as it did in our case, looked like as if these electrolytics were fine, you know, and I mean these are actually good quality capacitors. I mean these are, you know, the Rubicon capacitors, and they're not really associated with a poor quality brand. So again, over its life cycle, these have started to leak, but not obviously you didn't get that puddle round. So looking above as we did, you'd never know until you removed them and test them. And some of these capacitors did test okay on the capacitance meter, insofar as the capacitance, they got near the value, but when you touched the capacitor and warmed it up with your hand, the value changed remarkably. And the other thing is, it wasn't until you put them on the ESR tester to test the equivalent series resistance, they actually could find that the capacitors were stuffed. So you can get misleading results if you're using a capacitance meter versus an ESR meter. Anyway, these capacitors just blanket replace them. So I would say that if you get a switch mode power supply, probably it's best always to start replacing the capacitors on the board. Now I did take out one of these capacitors, these large electrolytics there, just to test to make sure that one, they'd not leaked underneath, and secondly that the capacitance as rated on the can was correct, and it was. But because I'd removed one, because they're in series with one another, it allowed me then to test the other one. So I did test that as well, and they were both reading okay. Normally capacitors of that size, you know, don't normally go or leak. They can do, and I've had some with the screw terminals on top where one of the terminals is slightly pushed pushed itself out, moved to one side and leak. But it's very rare actually, those capacitors do actually go. It's not entirely impossible, because I have had power supplies like that in the past where smaller versions of those have sort of dried up, but it's very rare, to be honest with you, in comparison to the output capacitors, the ones that do the smoothing of the output for the power supply. So yeah, that's a really good result, and as I say, you know, always start with the easiest first before, because you'll be surprised, you know, what it could be, and you don't want to lead yourself off down these little paths. Always worth removing them as well and having a look underneath to see if there's any leakages, because as I say, if it hides that, you'd never know, would you? So there you go. Right, what we'll do then, we'll test the radio now in the next part of the video to see how that works, see if there's any other faults on it and things that might need to be put right. So we'll do all that next. Okay, so we've connected it up now to the radio test that we're going to be looking at very shortly. We'll do a bit of spec testing on it, but first of all, let's just see if all the functions and controls work, things like that. So obviously we've got the frequency control knob there, seems to be working. Let's see whether we can go to different bands. Yeah, that's a bit dicky, that, pressing that in, and it's, oh, there we are, it's gone eventually. So it does look like as if, oh, sometimes that second button works and sometimes it doesn't. It's a bit fidgety. The 7 meg works, the 10, 14, does it go eventually? But it's very dicky, very sensitive, the switch, and it sometimes works, sometimes doesn't. The 18 megs was very difficult to press, and it's, yeah, that's definitely got a problem on it. Yeah, so it's obviously been well used insofar as, you know, many decades of this button being pressed. 21 meg, I can't get that at all. I can just about get the 24, 25 meg band. The 28 megs, no problem. 30 meg and the 50 meg. So that one's a bit awkward there. 21 meg, I've finally got it. So let's have a look. I'm not sure if that should work in this mode, but can't get that AB, the split button. Yeah, so I'm not sure if, oh yeah, so that's definitely got a faulty switch there. That's working. TS, that works. Can't get anything out of that one, but I don't know if it's meant to work that at this moment. That's a lock button, can't lock the control. Oh, now it's locked. Can I get it off? You have to press it for 1,000 years to get it off. Yeah, it looks like it. I've got SSB mode. Yeah, that's very dicky, is that. CW wide and narrow, or CW narrow. AM. I think there's different. That's not working altogether now, the AM, when I'm pressing that. And that's the FM. Two different modes in FM. So yeah, looks like I can't select the antenna either. I can get the attenuator, preamp, tuner, meter. Oh no, it's not working, it's a bit dicky. AGC, noise blanker. That one. What about the up down buttons, do they work? Maybe they don't work in this mode. I would have thought they would do, because it's in VFO. There's VFO memo mode, VFO, VFOA, VFOB. So I can't get these buttons to work. What's this? Medium wide cell. That's dicky. MVFO clear. Scan. Button's not working. Notch filter. So some of these buttons are working and not working. Anyway, what we'll do, we'll just go to the 50 meg band. I'll set it at 51 megahertz spot on. And then what we'll do, the RF power's wound down to a minimum. And we'll just have a look now at the radio test set. So let's see whether we can we can zoom in on the screen here and see what's going off. So let's have a look at that. And let's see whether we can see what power it's doing on FM and modulation. So let's just key up the transmitter. So we're getting 3.4 watts at 51 megs. It's just slightly off frequency, but we'll be able to adjust that anyway, and we'll go through that. Modulation 1, 2, 3, 4, 5. Yeah, got plenty of mod there. Radio test 1, 2, 3, 4, 5, 4. So I can see that. And 1, 2, 3, 4, 5. 5, 4, 3, 2, 1. Okay, so let's turn the RF power up then and see whether we get it up to 100 watts. So just turning that little knob that gets it up. So we've got 60, 70 watts there, 80, 90, 98.4 watts there then at 51 megahertz. Okay then, so what I'll do, I'll go down to the 3.5 megahertz band. I'm just on 3.5 megahertz FM, or we could just put it on CW, and then I'll key it up again on minimum power, and let's see what we get. Let's have a look. So again, 3.5 watts at 3.5 megahertz. Just turn the RF power up, and obviously we're getting to 37 watts there, 50, 60, 70, 80, 90, 102 watts. 5, 4, 3, 2, 1, 1, 2, 3, 4, 5. Yeah, the mod's there, as we can see. So yeah, 102 watts there, just on key. So he's certainly doing the power anyway, RF power and the mod's there. We'll be able to check the SSB as well, and AM obviously. But all looking good so far. So let's just do a bit of receiver testing now and see what it specs like on RX. Okay, so we've removed the front panel now, which is at the back here, off the front of the radio, and stripped that bit down. The front panel bezel, if you like, seems to come away with some difficulty, and I pried at it for some time and found that this is the PCB with all the switches on it. I've already removed some because we're going to replace them. There. So we're going to renew all these switches and that, but this is socketed. As you can see, there's some pins here, and that then plugs into the pins on this socket there, these two. So when you've undone all the screws for this section to come away, what you tend to find is then you're yanking at this bit here, trying to pull the front panel off, and it feels like as if there's another screw there that you've missed, and it isn't. It's just the resistance of these pins on this socket here, these two sockets coming away from these two. So yeah, it's a little bit of a learning curve is that, and obviously, you know, once you've freed that, then the whole front panel assembly comes away from the front. So obviously we're at the point now of unsoldering all these switches I've just taken out for all this area here, and we're just going to go through this laborious process now of replacing all the switches, and then obviously reassembling it for a further test. Okay, so we just spent a rather extraordinary amount of time replacing all these switches. Some of them have got different lengths plungers on them as well, like the switches that are for the keypad are slightly smaller in plunger depth than some of the mode keys, etc., which have got a slightly longer depth to them. So there's one or two various lengths, like these are longer ones that we've replaced as well. So it's about 3 different lengths of plunger. So these are all the old switches that we've replaced. As you can see there, been quite a bit to do. So yeah, we're okay. I think we're ready to rock and roll now. Put it back in its case, mount the case back on the front of the radio, which will be another interesting job, and hopefully, fingers crossed, the damn thing works when we power it up. Okay, so I'll turn the volume up, and put it on. Got 0.5 microvolt there. We're getting the receiver working. I'll just put the preamp on. So that's with the preamp on, so the preamp works. Preamp off. We'll just test the RF gen level. We'll set the squelch. And then turn the RF gen level up. Yeah, that's pretty good. We'll go to the 7 megahertz band, and I'll just put it on FM mode and go down to just bang on 7 megahertz dead. So let's do set RF 7 megahertz. Squelching out there with the preamp on again. So let's try the 14 megahertz band, 14.1, and FM now. It's off frequency, so it looks like the reference oscillator on the radio is off frequency because we're on 14.1 megahertz there, and the spec ain't too good. But when I adjust the frequency, you can see now the specs improved in terms of receiver sensitivity. So that proves that the receiver IF is, if you like, malaligned to the carrier. So we've got 14.1 megahertz sort of here, and the receiver's sort of here. And then by us adjusting that frequency means that we've aligned it. So that's subject to the reference oscillator. But the reference oscillator for the radio has moved off frequency. So that'll definitely need a look at that. So the receiver's off with its spec. Just go to 51 megahertz, and again, let's have a look at that. See whether we can get that spec. So set RF gen frequency 51 megahertz. It's quite good sensitivity. But yeah, I can improve the sensitivity again by adjusting the frequency on the radio. So if I come back down again and we'll go down to the radio. When I adjust this, you'll hear it. So it's got better there. It started to deteriorate. So it's not bang on 51 megahertz. It's sort of about there. So that will need tuning and what have you. So we can have a look at that as well. But I think first of all, before we go into alignment procedure, let's get this front panel off and have a look at these switches, see what's wrong, and go from there, I think. Okay, so we've got the radio back together again, and we'll just check all the buttons work now, obviously. So tuner button works, preamp lights coming on, yeah, attenuator, 10 or 1 or 2, meter, go between power, SWI, LC, etc. Automatic gain control lights coming on, the noise blanker lights coming on as well. So that's operating. Yeah, we've got little LED. The little LEDs on the buttons are a little bit faint to see, to be honest with you. That's the noise blanker off. That button's working as well. We've got SSB. Nice clicky buttons now. AM, FM, usual things. Dial's working fine. And We had all these as well. I don't know if some of these functions will work in this mode, but yeah, that little icon's coming off up there. These are for your memory things. Yeah, that's all working. That's your lock button, which is functioning now. I've got not sure if you've got A, B or what. I'm in sort of like in a different mode here. VFO menu, that's it. VFO-A, VFO-B, A equals B, etc. Not sure what that MW is. Maybe I have to go back to there. I think that's memory write, that's select, mem VFO, so these are all for memory, clear, and then the scan as well. So there's that. We've got up and down buttons there for megahertz, which is working. All the bands are working. Yeah, they're all fully functional. Nothing wrong with that. And then we've got these buttons here, and they all work as well. I don't know what, oh, that's the notch, and the little LED for the notch there comes on and off when we press it. So yeah, fully functional with the look of it. Not a problem. We've got a microphone, what they call it, Vox. When you press that in, and then you talk on the microphone, and it goes into transmit. As you can see, if I just tap the microphone, it goes into TX. So that's functioning. So everything seems to be operational. So I think the next stage that we'll do now is we'll go over to the alignment procedure now for that reference oscillator. We'll turn the test set on, we'll get the test set warmed up, as we should do, for at least half an hour for the frequency reference to become stable, and then what we'll do, we'll use this to transmit on, and then we'll align the reference oscillator which we found on the underside, which I'll show you next, and get the frequency accuracy of this unit back to where it should be. And then we'll do some more receiver testing, transmitter power testing, modulation testing, just to make sure that we haven't disturbed anything in doing the work that we've done. Back soon. Okay, so in the radio we're going to adjust the reference oscillator frequency adjustment. This is the Refos crystal, and that's the trimmer capacitor down there. So we're just going to go onto this trimmer capacitor. Obviously we've hooked the transmitter up to the radio test set, and we're going to be choosing 50 megahertz frequency, spot on, which we've done on FM. So I'm going to key up the transmitter. We've got the frequency offset displayed, offset of 290 Hz. So I'm just going to adjust this, see whether we can get it lower. And we're just getting it down now to 159, 163. So we're just gradually getting that down as much as we can. So nearly spot on frequency. Just going to do a full revolution on that capacitor, just in case it needs a bit of a clean up. There we are. Lovely. So that's netted that up nicely. Okay, so now we've adjusted the reference oscillator frequency for the transmit frequency side and receive frequency side. We've just also got another alignment to do on the FM side to do with this coil here, and that coil is the FM AM oscillator frequency adjustment. So what we aim to do now is transmit and get the FM AM oscillator to the correct frequency as well. If you like, there's two reference oscillators on this unit. There's one for the FM AM oscillator, and then there's also another one for the main VCOs, which are just adjusted. So let's key up the transmitter, and we'll notice that the offset currently is at 650 something hertz, on transmit. So what we'll do now, we'll just reduce that to as near on frequency as we can get it. So it's down at 27 hertz there, 16 hertz. You just got to be a bit, you know, careful with it, that's all. Just very minor adjustments, don't take much. We were down to about 5 hertz then, so I like to try and get things as near as damn it as I can. Creeping back up now. Only needs slight adjustments, very fine and minute adjustments. Notice we've only got a transmit power set at 10 watts as well, and that's for a good reason, so we don't overexert the RF amplifier. There we are, we've got it down to around about 30 hertz there, so I'm quite happy with that. Not going to play around with it too long. There's always a danger of cracking the ferrite cores as well in the coils, especially on older sets like this. You've only got to, you know, I've got a plastic trimming tool here, but if you're a bit too zealous with it and you turn it too quick or you put a bit too much pressure on, you can crack the cores in the coils. So, you know, you've always got to be very careful with that. But I'm happy with the frequency accuracy we've got now, both with in terms of the VCO and the FM/AM oscillator. Okay, so now we're on FM at 1.8 megahertz. Again, back to Rohde Schwarz radio test set. Let's have a look and see what power and frequency mod we get. As I say, we're on FM measurement now, so we're measuring the D mod in kilohertz here, what the frequency modulation width is. So let's test that, and we should be able to see the mod on the scope and the RF power. So we're getting like 102 watts. 5 1 2 3 4 5 5 4 3 2 1 1 2 1 2 1 2. Nothing wrong with that. Okay, so let's go to mid band then, the 14.2 meg. Select FM on the radio. Go to frequency there, 14.2 megahertz. Again, let's see what RF power that produces. 1 2 3 4 5, yeah. 1 2 3 4 5 1 2 1 2, plenty of power, and yes, we're getting plenty of mod. And then the 50 megahertz band. So again, 51 megahertz FM on the radio. So 51 megahertz. And what does it produce now? 1 2 3 4 5 5 4 3 2 1 1 2. Plenty of RF power, plenty of mod. So there is nothing wrong with that radio at all in terms of specification for transmitter power, transmitter mod on AM, FM, SSB, likewise on the receiver sensitivity, AM, FM and SSB on all bands. Absolutely superb, you know, radio. So that little radio there, we are going to put some anti-tamper seals on it that the owners requested, to prevent anybody from going in it and messing about, obviously, if a radio gets sold, so that it prevents people harvesting components. And, you know, right now it doesn't work when it does, clearly, as it's been tested here. So gives the owner of a radio confidence when it comes to sell the radio that you know, they're selling it in good faith, along with the anti-tamper seals, and they can point them towards this video if I want to as well. So at least that way then it's an assurance that the radio works. A very nice radio, very good. Been around a fair while of these transceivers, but testament to the build quality, the design, the construction that's employed within. You know, you can't do better than these sort of radios. The older radios are always the best, in my view, than these modern. I've got, you know, some modern radio gear here as well, you know, with band scopes on and things, but I always prefer, you know, the older sets more than anything. I like the design and the layout and the way the buttons work, rather than being software driven and having all fancy touch screens and things like that. You know, it gets too easy if that's the case. So yeah, this radio really good. I like the fact as well this knob is weighted. This is a solid like metal knob. It's not a plastic fantastic thing. It's got a very nice feel to it, a very nice free running, and it's you know, it's substantial as well. It's a very nice feel to it. I like the clickiness of all the switches and buttons and things. When you press them in, you know you've pressed them in. You know, everything has got a nice clunk click to it. And all the knobs and everything, it's not too crammed up. The trouble is with a lot of these modern transceivers these days, everything's all crammed in, and every button's got 20 functions to it, and you've got to have a PhD in operating the radio first before you can get any enjoyment out of it. This is sort of, you know, just straight in. Even somebody with basic radio experience can operate this radio without a problem. And of course, you know, such a simple radio, but yeah, packs a punch. I mean, you know, over 100 watts RF power in a little unit like this, and it's designed to work that power as well over a long period of time on high transmit duty cycle. Don't forget, a lot of these older transceivers use bipolar RF power transistors in them, as opposed to these FETs that we've got in modern equipment today. And the problem with some of these FET designs, RFPAs, the way they're biased and everything, is that even when the transceiver's only doing a low level of RF power, the amount of quiescent current taken by those FET amplifiers can often overheat them. And I've seen quite a few of these modern ICOM transceivers that have come in, and Yaesu transceivers, the very latest transceivers that have just fallen out of warranty, that have been sent to me for repair, where the FET has actually unsoldered itself off the board, the RF power FET, because it's got so hot. And some of the designs they're using these days now, they have a FET soldered to the top of the PCB, and there's all copper stitching through the PCB itself, and then the bottom of the PCB fastens to the heatsink on the bottom. So rather than having the FET device directly bolted to the metal heatsink of the transceiver like older designs like this had, quite often now they're going for the FETs that are soldered to the top of the PCB. It uses a PCB to conduct heat in order to get to the heatsink underneath. There'll be a silicon pad or some heatsink compound that will just, you know, try and wick that heat away. But the PCB, even though there's lots of copper traces going through and lots of copper stitching there in that area, ultimately what happens there is that the PCB can't wick the heat away quick enough. And those type of radios are okay on short transmissions, you know, where they're transmitting for a little bit of time, a very short duty cycle, but they're not designed for long transmissions. You know, if you key the radio up at maximum power and in the CW mode or in FM and you're transmitting, having a right old natter to somebody, that transistor can burn out quite easily. And you know, it's often the case as well with the ICOM ID52 handheld that I've here. This thing, great little radio on D-Star digital, but when you're transmitting for a long period of time on this transceiver, what happens is because this has got that FET design that I've just spoken about, the transceiver overheats, and it's got a temperature sensor in it that detects when the transceiver's overheating. So even when I've got this on low RF power, and it's, you know, it's on its lowest RF power, the problem I've got with it is that it shuts the transceiver down. I can't talk on it till it's cooled down, you know, and again it's got that FET in it, an RF power FET. Now if I had a bipolar power transistor bolted to the heatsink direct, the heat would wick away a lot quicker. But this has got that design again employed, where the transistor is mounted on the PCB, not bolted to the heatsink, and so it doesn't take long for the transceiver to detect a overheat condition and shut down. And this is a problem with these modern transceivers. You know, they're not like the old school stuff, and that's why I like the old school bits of kit. You know, and again, this is a D-Star transceiver, digital as well as analog. But yeah, so I think it's been quite an interesting video. We might do some off-air testing now and just see what it's like at reception off-air, and see how that goes. Okay, so now we've shifted frequency to 1.8 megahertz. Again, AM amplitude modulation. So let's see how much power that it does there. 3, so 117.5 watts. So that's very reasonable, isn't it? That frequency range. So that proves again on amplitude modulation that we're getting that sort of RF power. So let's move on to other measurements. Okay, so let's do it an AM test now on amplitude modulation. So we're on 51 megahertz AM now, mode on the transceiver, as you can see there, AM. So let's see what the radio test set can give insofar as that's concerned. Bit of a shadow on the screen there, it's a pain. Right, there we go. Right, so 4, 3, 3, 3. So yeah, 93.1 watts. So that's pretty good. AM mod depth at 51 megahertz, 93.1 watts. Nothing wrong with that. Okay, let's see what it does now at 51 megacycles and 51 megahertz. Upper side band. Let's see how much RF power we get out of it now. 4. So again, top of the frequency band now, the very upper limits of the frequency range of a transceiver. We're getting 131.2 watts RF power. So that's a good indication that the transceiver at its lowest frequency range of 1.8 megahertz is well into the 100 watts range, and indeed the highest frequency at 50 megahertz is 131 watts. So you can't grumble at that. It's got certainly a lot of punch in it on SSB. So there you go, proves a spec on SSB. Okay, so let's see how much power we get out of it on 1.8 megahertz now, the lowest frequency. So here we go. 5. So that's 117 watts at 1.8 megahertz. So I'm quite happy with that. I mean, we prove that basically the bands, insofar as SSB are concerned, are doing absolutely wonderful with regards to transmit power. 117 watts on 14 and 1.8 megahertz. That sort of proves the the bandwidth. But the power amplifier is okay, so looks good. Okay, so now we're going to hook the radio up on this test frequency of 14.2 megahertz LSB. We're going to hook it up to the Rohde Schwarz. I'm just going to see whether we can magnify on the screen a little bit so we can see the power. So what I've done, I've set this test up now on the Rohde Schwarz, because Rohde Schwarz has got the capability to read clearly the peak RF power, the PEP, for both AM and SSB. So what we've done, we've set a measurement up now where we're measuring peak envelope power, as we can see on the left here, PEP. We're also making the time automatic, so the detection time is automatic. We've got a power range hold, so the maximum RF power that comes out the transceiver will be captured on the display when I modulate the signal. We've got the RF power wound up to maximum on the front of the radio, and so I'm going to begin my measurement, and the RF power will be read here where it says milliwatts there. That'll change to watts, and we'll see what peak RF power this radio can do. So here goes. 4. So that's like 135 watts RF power which has been captured there. So that's what we're getting on 14.2 megahertz. So that's pretty good, there's nothing wrong with that. 135.2 watts is exceptionally good for this transceiver. So what we'll do, we'll have a look at it on another frequency range. We'll play to it on, say, the 1.8 meg band, and see how much RF power we get out of it, and then we'll do the same at sort of 50 megahertz, I think. That'll sort of do it low, mid and high, more or less. So yeah, that'll be a good indication. Okay, so we set a measurement up now at SSB testing, lower sideband, 51 megahertz. So I'm just going to introduce the RF signal itself. Got a 500 hertz tone that we're modulating the carrier with. So there we are, that's the recovery of that. Nothing wrong with that. That's the sensitivity. The signal can be heard well into the 0.1 microvolt range. Okay, then we'll go to upper sideband testing now. So we'll select upper sideband and we'll go to upper sideband, and we'll just check the tunings there. It is indeed. See how the sensitivity is like. Nothing wrong with that. Okay, so what we'll do now is we will change the frequency again to the 1.8 megahertz band. We'll go to LSB, signal there, and we will now just move back to LSB on here, and we will do RF10 frequency 1.8 megahertz, and we will turn the RF on. And as we can hear there, you know, modulation level. Yeah, you can still hear tone there, well into 0.1. Nothing wrong with that. Right, let's do upper sideband. Check the level again. Yeah, nothing wrong with that. Okay, what we'll do now, we'll just go to somewhere probably mid-band, like 14.2 megahertz. We'll go to upper sideband, so we'll go to lower sideband. We'll then go here, click this to lower sideband, RF10 frequency, 14.2 megahertz. Modulation level. Nothing wrong with that. So we're upper sideband testing. That's all there. Modulation level. Yeah. Okay, so basically we proved there that the FM works, the AM works, the SSB upper sideband and lower sideband, they all work across the entire frequency range of the receiver. So we've done all those receiver tests now. Let's do some transmitter tests, see what we get. Okay, so we'll just do two sort of up and lower frequency band measurements on AM. So an amplitude modulation now, we're on 51 megahertz. What we've done is we've set up the RF gen now to 60% modulation depth for AM. So I'm going to introduce the carrier. So we've got good sensitivity there. We've got the squelch set on the transceiver. There's nothing wrong with that. I mean, it squelches out at like 0.1 of a microvolt there, look. Just under 0.2, so that's pretty good. Nothing wrong with that. Right, what we'll do now, we'll change to the 1.8 megahertz band. We'll select AM on that, and then we will go to 1.8 megahertz. RF gen frequency 1.8 megahertz, and then we'll select the RF level, and already we were getting a receiver sensitivity coming in. Yeah, nothing wrong with that. Yeah. So as far as AM is concerned, that's fine. So let's do some SSB testing now then, and we'll go to lower sideband and then do some lower sideband, upper sideband testing on the sort of 50 megs, and we'll do that and see what we find. Okay, so the first thing we'll do some measurements on FM on receiver sensitivity first. So we've got a breakout screen here, which is of the Marconi radio test set down there. So to let you see it clearly, we set up a frequency for testing of 51 megahertz. We're just generating a signal now. We've got the radio squelch setting so that it mutes the radio at minimum level. So we're just going to see what the receiver sensitivity is here. We're looking around for about 0.3 of a microvolt roughly for the sensitivity for the squelch to break, and we've got that as 0.287 of a microvolt, so that's pretty good. Radio's certainly not deaf, it's very good performance is that. Yeah, nothing wrong with that. Okay, fair enough. Right, okay, so let's move band then to say 28 megahertz, and we'll just set the dial now to 28 megahertz diode, put it on FM, and then we'll set up the receive frequency here to 28 megahertz. And so we basically got the receiver, as you can see there, 28 meg set up as well on FM. So let's just have a look and see what the receiver sensitivity is like on here. So that's still good. Yeah, nothing wrong with that. I'll just put the preamp on. The preamp's vastly increase the sensitivity. Yeah, nothing wrong with that at all. Okay, so we'll go down to 24 megahertz. I'll put it on 24.9 megahertz. Look, switch it to FM, and then we'll go on to here. RF gen frequency 24.9 megahertz. RF gen level. So yeah, pretty similar spec to before. Nothing wrong with that. Let's go down to 21.3 megahertz. So again, we'll set the radio to FM on 21.3 megahertz, and then ultimately the test set as well, 21.3 megahertz. RF gen level. Yeah, half a microvolt roughly. Okay, so let's go down to 18 megahertz. I'll set it to 18 megahertz dead as a spot frequency. So there we go. Put it on FM. So set that up on the radio, as you can see, and then ultimately on here now. RF gen frequency 18 megahertz. Yeah, nothing wrong with that. Let's go down to 14.2 megahertz and FM. So we've got the radio set there. Let's go up to here. RF gen frequency 14.2 megahertz. RF gen level. Let's have a look. Yeah, similar sensitivity to before. Check the RF gain works. Yeah, it does. So that's good. 10 megahertz. We'll set it to 10.1 megahertz on FM. As we can see, 10.1 megahertz FM. And then what we'll do, we'll just go back to here and set up RF gen frequency 10.1 megahertz. Nothing wrong with that. So this is a 7.2 megahertz frequency. I'll choose that on FM. So it's just to guide us really on receiver sensitivity. Megahertz. Yeah, nothing wrong with that. And then the 3 meg band, I'll set it to 3.5 megahertz on FM again. So we've got that set up there, 3.5 megahertz. And then we will do the RF10 frequency, 3.5 megahertz, RF10 level. Yeah, and with the preamp on, increases the sensitivity even further. Yeah. Right, so that's okay. Let's try the 1.8 megahertz band now on FM. So let's do that. 1.8 megahertz, RF10 level, and then let's see what's coming in. Yeah, that's okay. Obviously with the preamp on. Yeah, nothing wrong with that. So yeah, just turn the squelch up to see what level of RF level you need to break through the squelch. So that's with the squelch wound up really tight, and I'm just seeing what level it'll break through at. There we go. Yeah, so quite pleased with that. Very good receiver performance, and we can progress on now to doing some other measurements on AM and SSB, see what that's like. In addition to that, if we have a look at the microphone, this ICOM HM33 microphone, you've got the up and down buttons on the top of the microphone as well, so you can press and hold it, and obviously it'll zoom frequencies up and down as well, so that's good. We've obviously got a press to talk on it, little mic hanger as well, so you can hang it up somewhere. Quite a nice microphone, very good indeed is that, a genuine ICOM microphone. So we'll have a look round the back now and see what credentials it's got round the back. Right, we'll switch the mode to upper sideband now, so we'll do the same testing.
1, 2, 3, 4, 5. This is a test. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1. Testing, testing, upper sideband, over.
Okay, so we've got a monitor receiver on the other bench, 251 megahertz. We're doing some speech testing now on LSB, just so you can hear what it sounds like on the other radio.
1, 2, 3, 4, 5. This is a test. 1, 2, 3, 4, 5. 5, 4, 3, 2, 1. Testing, testing on lower sideband. This is a lower sideband. Over.
Okay, so now we're at 51 megahertz FM here, right at the complete upper end of the spectrum that radio's capable of dealing with. So what we'll do, we'll zoom in now again on the screen on the radio test set, and we will key up, as we keyed up now, 51 megahertz at 3 watts, and we'll start to increase the RF power. So here we go. Just over 10 watts, 19, 15 watts there, 25, 31, 36, 46, 53, 64, 77, 91, and right to the top there. So we've got 101 watts there of RF power on FM. So not bad at all then. Can't grumble at that. Okay, so we'll do the same test now on FM on 1.8 megahertz. Doing the same RF power measurement, so we'll just have a look there. We're going to key up the transmitter on 1.8 megahertz. As I say, I've got the modulation there when I'm talking to the mic. So I'll just turn the RF power up, as you can see in the top right hand corner of the screen. So, you know, we're currently over 30 watts now and approaching. Just keep turning it up. And there we are. So we've got 109 watts there on 1.8 megahertz. So we'll unkey the transmitter. And we'll do another test on, I think it's 50 megahertz now. We'll see how much power it does on there. Okay, so now what we're going to do, we're going to do a transmit power measurement using the RF power control just here. We're going to turn this right up. We're in FM mode at the moment, just for ease of the measurement. We're on 27.800 megahertz, 27.8. And we've got the radio test in auto tune, so if I key up the transmitter minimum power, we're observing on the radio test set there 2.8 watts. And we've got the mod there on the scope, as you can see when I'm talking to the microphone. And we'll just focus in now on the RF power a little bit. I think we might be able to see that a little bit better if I just move that a bit. Now what I'm going to do is I'll focus in on the display where you can see a bit better. And as I say, we're in the top right hand corner just here. That's where the wattage is now. I'm just going to turn that control up now and we'll just observe the RF power. So, and we're getting right up to 104 watts there. Look, 104. So that's pretty good. Still keyed up on the transmitter, and then we unkey. So that's just shows you how much RF power this radio can do. So key up again, and then again 104 watts RF power. So pretty good.
So we're stuck on 575 now, but I don't think there's no till 2 meters. I've got little 52 sat here and I've not seen no come through. But, I'd only got this dashboard going and I just happened to have that sounded like you. But I've just sat there just finishing my tea at this time at night. Anyhow, try and catch you tomorrow, mate. You take care and look after yourself and don't work too hard on that SDAs. Yeah, 7-3, no problem. We'll catch you tomorrow. I'm not doing a can't wait. I've only worked about half an hour. So it's really don't want to too hard on that imp. I don't know when you're injured. And I'll speak to you tomorrow. M9 IOU. I'm not working on it. No way. It's that bloke's coming Tuesday. He can sort it out.
CQDX, Italy, Uniform 6, Victor Hotel Sierra. CQDX, CQDX, CQDX. Italy, Uniform 6, Victor Hotel Sierra. I am listening for any calls.